Hello everyone. Can all of you hear me clearly? Are you able to hear me? Okay. Very nice. So you are welcome to actually start a audio conversation. Just interrupt me anytime you want. It will be good if we have an interactive session. It helps everyone. So we will be discussing.
What is today's topic?
Yeah, last time we talked about geometric transformations. Uh, Today, we will be actually talking about a problem which is more related to combinatorics than geometric transformation. So, this is quite a beautiful problem actually. So, if you have a pen and paper, that will be very helpful. So, this particular problem is something like this. We have this notion of permutations, which is basically rearranging numbers. And we'll be talking about a very special type of permutations. Let me tell you what that is. Suppose we have five numbers. These five numbers are A1, A2, A3, A4, and A5. And it's given that A1 is less than A2, A2 is greater than A3, A3 is less than A4, and A4 is greater than A5. This is the given data. So this problem came up in a recent ISI entrance, but it is also from an Olympiad that came up that was in USSR about 30 years ago. So it's a very popular problem. Like it's a very standard problem in mathematics. So it's not a very weird problem or anything. So we have this. These are called alternations sometimes. Alternations. So can any of you give me an example of an alternation using the five simplest numbers 1, 2, 3, 4, 5? Give me a sequence which is an alternation using these five numbers 1, 2, 3, 4, 5. You can speak it up or you can give me in the chat. It will be harder for me to give it in the chat. Yes, this is a topic from combinatorics. So it is definitely combinatorics is very relevant in RMO. Okay. So using the five numbers 1, 2, 3, 4, 5, can you give me examples of alternations? So what you have to give me is the value of A1, the value of A2, the value of A3, A4, A5, where these numbers are these numbers, provided we have this property satisfied. So for example, we could have A1 equals to 1, A2 could be 3. So A1 is less than A2, that is satisfied. A2 needs to be greater than A3, so A3 could be 2. A3 could be 2. Then A4 could be 5. And A5 could be 4. So notice what happened. A1 is less than A2. Okay, that is satisfied. A2 is greater than A3. Okay, that's satisfied. A3 is less than A4. Okay, that is satisfied. 2 is definitely less than 5. And A4 is greater than A5. A4 is greater than A5. Well, that is satisfied. 5 is greater than 4. So all of the conditions that we want are satisfied in this particular sequence. So we say that 13254 is an alternation. Is an alternation. Can any of you give me example of another alternation using the same numbers? You can think of this as an up down up down. So visually you should think about it like this: up down up down, like this. Okay, so you have 1 3 2 5 and 4. Do you see why it is up down up down? It's called a zigzag number. You see why it is up down like this, right? Okay, so can you give me another example of an alternation? Okay, so Raghav is giving us another example. Let's see what his example is. He is saying that this is 24351. Let's see if that works. 24351. See, if I write like this, it's very easy to see that it is indeed an alternation. It's sort of a very visual way of thinking about the numbers. Do you see that? Do all of you see that? There is a notations are very important in mathematics. When I was writing, you can check this out. I mean, when I was writing 13245 if I write 13254, I have to sort of work hard to see if these numbers are indeed alternations. But if I write 13254, you immediately see that this is an alternation. Do you see, all of you, what I'm saying here? This is not an accident. There was a mathematician called Von Jones. In fact, he discovered something called the Jones polynomial for the knot theory. And he also came up with this many-dimensional, multi-dimensional symbolism for mathematics. It's very beautiful. You can go and look it up. Von Jones actually died very recently, and Terence Tao wrote something on his about him very recently, and he was talking about this multi-dimensional way of writing formulas, how that can help us to sort of uncover more of mathematics. So I mean, anyway, you can go and check that out. So the question that we want to ask is, how many so this is the question, how many alternations are possible? How many alternations are possible with 5 numbers? 5 distinct numbers. Okay, now one thing I have to say, that it could be up, down, it could be like this, or it could be down, up, like this as well. So can any one of you give me an example of a down, up alternation? It is right, Srijit. That's correct. 12354. Okay. Someone, Dr. Dattatreya Dhobale actually gave us this. So let's write that down. 12354. So this is not an alternation. That's a problem. Yeah. So how many alternations are possible with 5 distinct numbers? This is a question. A very related question came up in the ISI entrance of this year, as I said at the very beginning of this talk. So this was the answer is not 5 factorial, definitely, because not all permutations of 5 numbers not all rearrangements of five numbers are alternations. So think a little bit more, everyone. Think a little bit more. This is a very, very interesting problem in its own right. It's not 5 factorial. No, it's not 5 factorial. So I'll give you a minute to think about this. In the meantime, let me remind all of you that you can go to chinta.com to register for the Bose Olympiad that is coming up in the 1st of November. It will be a very good practice for IOQM as well. If you are an internal student of Chinta, of course, you probably have already registered for it. If you have not, please do that. Do it right away. And if you're an external student, you can also register for the same. It will be a very good practice for IOQM, and students from different parts of the world will be appearing for it. In last time in summer, about 251 kids appeared for that. In fact, we had about more than 600 applications. So it's a very good pool. Okay. This is also on YouTube Live. Yes, that's correct. All right. So anyway, can anyone think about this? So this is a very simple problem. I mean, there are multiple ways of doing this problem. Let me give you one way. Okay. So one way, which is sort of a dumb way of doing this problem. One way is this. So you start with 5 numbers, A, B, C, D, E. Okay. You start with 5 numbers and you sort of brute force your way through this. Brute force your way through this. So if you have 5 numbers, how do you go about it? Well, if you have, so again, think of this spatially. Think of this spatially. So you want, right. So you want A is less than B. Suppose, so you want A, you want this, you want it like this. You want zigzag like this. So just let's work with this one, up, down, this one. And then the other one will be exactly similar. The other one will be exactly similar. So what we can do is, we need, suppose A is less than B, so we can just put it like that. Now what about C? Well, we know that C is less than B. Now I want you to think about this visually. I said that earlier. So I'll draw it like this, just to, I mean, during the exam you won't do it like this, but just to think about it, you should think about it like this. A, B, and then you want C. So how do you do C? Okay, you know that C is downward, but the question is how much down? So maybe it's here, or maybe it's here. Can anyone tell me, what do I mean, visually speaking, what do I mean by these two different positions of C? Can anyone tell me that? What do I mean by these two? Sorry, someone was speaking. Go ahead.
Sir, can I try?
Yeah.
So basically, what I think is like when it is in the above position, like is in the upper position, that means that C is less than B but greater than A.
Ah, excellent. So C is here. Okay. And what about
if
this?
It is lower, then it is smaller than A and smaller than B as well.
Great. Excellent. So these are the only two things that is possible, right? Okay, so let me draw this. Great. Excellent. Now let's talk about D. So we know that D should be up. So how many positions for D are there? So if we let's look at this one, the first one. Okay, so let's use green. And this is a very important picture, because later I will ask you a question, a different type of a solution for this particular problem. There is a bijective solution, but this this particular picture is kind of suggestive of that. So let's go it take it one step at a time. So we know that D is here, right? D is above C. So let's take the first position of C here. So I can draw it like this, or I can draw it like this. So this is D or this is D. What does these two position mean? Well, it means that we either have A, C, okay, maybe I can change the color. We either have A, C, B, and D is between C and B. That is fine. Or we have, okay, so this is D, correct. Or we have A, C, B, D. I'm just color coding the entire thing. Just a sec. Okay. I'm just color coding the entire thing. Let's see how it works out. All right. What about the other C? So for the other C, what we have is, can anyone tell me how many positions will I have to draw for the other C? I want to draw D. So I can either draw it here, which is like this, which is, okay, so maybe I can draw the picture like this, which is like this, A, this is D, or like this, D, or like this. If any one of you have seen staff notation for piano, you know exactly what's going on. It could be below the staff, that is below the A line, or it could be between A and B line, or it could be above B line. Do you see that, all of you, what I'm saying? So again, I'll write C, A, B. So this is D. Or we could have C, A, B, and this is D. Or we could have C, A, B, and this is D. Okay? So we have 2 plus 3. I'm brute forcing it. But this particular situation this particular picture will help us to do the next time. Oops. Just a second. Okay, so this is okay. So finally we have this 5 things. Now we have to talk about E. I think all of you can tell me how many positions will E be, can E be. So E has to be less than D. E has to be less than D. So you have to figure it out now. We have 1, 2, 3 positions for E for the first one, right? 3 positions. 1, 2, 3, 4 positions. Do you see how I am marking the gaps? Do you see that, all of you? We have 1, 2 positions here for the E will be smaller than D, so this is okay. We have 1, 2, 3 positions here, and we have 1, 2, 3, 4 positions here. So 3 plus 4 plus 2 plus 3 plus 4. How much is that? Anyone? This is 16. So this up down is 16. Up down is 16. And by symmetry, down up will also be exactly 16. So this is 16, this is 16. So in short, the number of alternations of 5 numbers, alternation is alokik, this is down up or up down. What kind of arrows we have here? I'm using alternations for both kinds. So this is I'm responding to this comment by Alokik Tiwari in YouTube. So when I say alternations, I do up down or down up. I'm using both of them actually. Okay. So this is total 32 cases are there. And brute force is not the best method, of course, but this is a method of doing it. The question is, how do you do it without brute force? Now, this is something that I'll ask you to think about. We will be using this picture. So take this picture as a clue, and you can use this picture to create a sort of a bijection. So you have to think about bijection to actually do this problem. I'll give you an example of what I mean by bijection. So that you can, just a second. Just a second. So this is, one more please. This is very, okay, that's better. Okay, so what is bijection? Let's talk about that once. It's very simple, but it's very powerful. Bijection is a principle that is used to count elements. And it was initially, it was first popularized by Cantor, who was trying to compare infinities. And even if when you are not comparing infinities, you can still use bijection very effectively. For example, if you want to know how many people have visited theater, suppose you want to know how many people have visited a theater, how will you count the number of people that have entered the theater during a particular presentation? Well, you can go to every seat and try to count every human being. You can go to every seat and exactly, Raghav is correct. You can go to every seat and try to count every human being, but then it is very difficult, because someone might have visited the toilet, someone might have left the theater early, or you might have double counted some people. So here are the set of people who have visited the theater, and here is the set of tickets sold, as Raghav pointed out. So there is a bijection between the set of people who have entered the theater and the set of people who have purchased the ticket, assuming that every person have purchased one ticket and every ticket is purchased by exactly one person. So this is the fundamental idea of bijection. It is a one-to-one onto mapping between two sets. Here the set is set of people, and here the set is set of tickets. So what Cantor said is that if two sets are bijective, then you can say that they have the same cardinality. That means they have the same number of elements. But this actually produced very weird type of results. What type of results? I'll give you an example. Cantor found that if you say that if there is a bijection, that is a one-to-one correspondence between two sets, and if you claim that means that the two sets have the same number of elements, then you kind of end up with something very weird. Let's take all natural numbers. Let's for the moment, let's take positive natural numbers. The set of positive natural numbers, all of them, infinitely many of them. And let's take the set of all the even natural numbers, 2, 4, 6, 8, 10, 12, and so on, there is a one-to-one correspondence between these two sets. It's not a paradox. This is even. So what Cantor said is kind of paradox. Yeah, you're right. So there is a map from natural numbers to even numbers. So for every natural number, if n is a natural number, you can make it double to get 2n, the output number. That's an even number. And for every even number, you can get a unique natural number back in the set. So you can just half it. Take an even number to get its preimage, just half it, and you'll get its preimage. So this is a two-way map. For every natural number, you have a unique even number, corresponding even number, it's double. And for every even number, there is a unique natural number, it's half. So there is a bijection between natural numbers and even numbers. So Cantor said that the cardinality of natural numbers is equal to the cardinality of even numbers. This is very weird because we see even numbers as a subset of natural numbers. It's of course subset of natural numbers, and it's mind-boggling why a proper subset can have same cardinality as the main set. This is totally weird and mind-boggling. But this kind of interesting and very powerful stuff was done by Cantor. And we use, for the finite case even, the bijection principle is very important. We discuss it at length in our Maths Olympiad program. The internal students have probably, some of you have already attended it. But even if you have not, you should definitely look it up in a beautiful, there are very beautiful combinatorics books. One book that I would particularly recommend is Principles and Techniques in Combinatorics. This is I don't remember the name of the author. I think it is Ko Ki Meng. Yes, that's right. It is Ko Ki Meng. That's correct. It's a Vietnamese author. It's a very, very beautiful book. You can look into it. And there is another book called Theory of Combinatorics. If you are really interested in looking into some very beautiful book, this is by Venkatraman. So Venkatraman wrote this book in, this is a black cover. The book is of black cover, and it's such a beautiful book. What happens is every chapter of this book starts with something called forerunner problems. We try to do it sometimes in our program, not very successfully, but we keep on trying. So if you are able to do those forerunner problems, and those are doable just by thinking about them, then when you enter this chapter, you see that the theoretical part of the chapter is almost done because you have thought about the problems so much. That's how the problems are devised. And then there are some problems, follow-up problems of that. So there is this forerunner problems, theoretical discussions, and then follow-up problems. Very beautiful book. You should definitely look it up. All right. For today, we will stop out here. I will be meeting you next week again. And till then, take care and think about the problem, how to solve that alternation problem using bijections. Okay. Bye, everyone. Take care.